Hello, my name is Ashlyn Harvey, and for the spectral analysis problem, my problem is problem J. To begin, let's talk about what we're working with. So, what we're working with? The formula that I was given for my problem is C10H12 and then an oxygen molecule. The first form of spectroscopy or spectral analysis that we're going to use is IR spectroscopy. As we can see, this is the unmarked image. Before we talk about what I found, I want to talk about why it's important to use this and how this helps us. So, why do we use IR spectroscopy? The image above or before was the graph for IR, which is short for infrared spectroscopy. This form of spectroscopy is used to identify functional groups like alcohols, carbonyls, or amines. How do we determine this? Well, we determine this through each functional group having a different vibrational frequency and resulting in different peaks on the graph. So what did I find? I found three things worth noting on the IR spectroscopy. The first thing was marked at 1390 to about 1465, which is the methyl group. The second thing I marked is the carbon that's double bonded to the oxygen, and this was found around 1710. At this point, it's a carbonyl group. We don't really know what we would be looking for. However, in this example and based on the graph we were given, we know it's likely a ketone because there's not a second stretch around 2700 or 2800 like we'd expect to see if an aldehyde was present within the sample. And then the third thing I marked was alkyl groups from 29 to 31. Here's an image of the marked graph. You can see the methyl group, the ring that's present, the carbon that's double bonded to the oxygen, and then those two alkyl groups later in the graph. The second one that we looked at was the 13 carbon NMR spectroscopy. Here is the image that I was given. Again, just like the format with the IR spectroscopy, I wanted to look a little bit into why we use this first. So why do we use this form of spectral analysis? This is one of two NMR techniques, and this helps us determine the environment of the carbon atoms in the molecule. It helps provide detailed information about functional groups that are present, carbon-hydrogen connectivity, stereochemistry, and helps to determine the unique carbons within the molecule. So what did I find? For this image, I marked each peak with the carbon that relates to the corresponding environment. Around 30, I marked a unique carbon that's bonding environment looks like a CH2 bonded to a methyl group. At 45, the carbon is bonded directly to the ring. Around 127 to 130, there's a mark where we see the carbon, the CH group bonded to the aromatic group. And then the next peak around 140 is similar to the one before, but there's an extra carbon, so it's a carbon, a CH group, and then it's the aromatic group. And then the fifth peak that is marked is at 207, which is that unique carbon where it's double bonded to the oxygen. So here's the marked graph, kind of going through and pointing out what I had talked about in the last slide. The last form of spectroscopy is the 1-hydrogen NMR spectroscopy. Same thing here, we're going to talk about why it's used and how it's helpful in determining the structure of a molecule based on the formula. Again, so this is the second type of NMR spectroscopy that's used, and this is used to determine hydrogen bonding environments, integration, multiplicity or splitting, and connectivity. So what did I find? For this image, you'll see that I marked 3 different hydrogen peaks showing 3 unique protons in this unknown molecule. At 2 ppm, there's an alkyl group, alkyl CH3 group. The integration of this hydrogen is 3H and the splitting is a triplet. At a peak around 2.5 to 3.0, another alkyl group, but it's a CH2 carbon group. Integration here is 4H, and the multiplicity is a quartet. And then the final peak around 7 to 7.5 ppm would be indicative of that carbon ring. This integration is 5H, and the multiplicity would be a multiplet. So here's a marked graph for the hydrogen NMR. And then on the next couple of slides, it's just going to be talking about how I organize this based on the data and the tables that were given in the document. So this is a table that I used for the IR spectroscopy just to keep everything organized. The 1390 to 1465, that methyl group. The 1500 would be that benzene or that ring. The 1710 is indicating the ketone, and then the 290 to 31 is that alkyl group again. And that alkyl group helps with indicating CH2 and CH3 carbon stretching within that ring structure. The second table is the 13 carbon NMR table. In this table, there are 5 unique carbons that were present on the spectrum. Again, like we talked about, the chemical shift at 30, the bonding environment, chemical shift at 45, that unique bonding environment, and so forth for 127, 140, and 207. And then the final table is the hydrogen NMR, and this is demonstrating the chemical shifts, integration, and splitting of the various hydrogens within the molecule. Like we talked about before, there's the 7.1 to 7.4, which is that 5H multiplet that's indicating the ring, or the benzene in this structure. 2.5 to 3.0 is that quartet, that 4H, it's looking at the CH2 group. And then 2.0 is that methyl group, which would end up splitting into a triplet. So all of this information helps us to determine what this sample might be based off of the molecular formula. And I concluded that this would be the proposed structure. And the IUPAC name for this is 1-phenylbutanone. And that concludes my spectral analysis problem explanation video. Thank you.